quantum strategists, and welcome to the Quantum Wargaming channel. My name is Alex Candeman, and my personal journey into quantum computing came after 2 decades in business strategy and innovation. When I started learning quantum computing, I had to revisit the advanced topics of math, physics, and chemistry from my PhD days. It is clear that for business leaders, especially for those without a technical background, mastering these topics could be quite challenging. I, however, firmly believe that with the right approach, quantum computing can be taught without the use of advanced math and chemistry and physics. In today's video, Anna and I will introduce you to the basic concepts of quantum computing. We will minimize the use of math and will focus only on the aspects of quantum computing that are important for business leaders and managers for making decisions.
Hello. I am Anna, Alex's AI sidekick. He thinks that I am an expert in quantum computing. However, I am just learning. Please don't judge me too hard.
Let's start with the definition of a qubit and a bit.
A bit, also called binary digit or classical bit, is the smallest unit of information in classical computing technology. A bit can have only 2 values. It can be either 1 or 0. A quantum bit, also called qubit, is the smallest unit of information in quantum computing. Qubit can be 1, 0, or simultaneously 1 and 0.
This remarkable property of a qubit called a superposition. Superposition is not about uncertainty whether the qubit is in state 0 or 1. Superposition means that qubit is simultaneously in both states 0 and 1. In mathematical terms, that could be expressed that any given qubit psi could be expressed as a linear combination of state 1 and state 0s, with alpha and beta being respective amplitudes. Alpha and beta are complex numbers, but this should not concern us in this course. What's important to understand is that upon measurement of the qubit state, the probability that we will measure 0 is exactly equal to alpha squared, and the probability of qubit being in state 1 is equal to beta squared. Now let's explore how this superposition property allows quantum computers to store and process information in fundamentally different ways, and how this property allows quantum computers to gain substantial advantage over classical computers. We will start with quantum information density.
Quantum information density refers to the amount of quantum information that can be stored or transmitted per unit of physical resources, such as the number of qubits or quantum bits required to represent a certain amount of information. It quantifies how efficiently quantum systems can encode or process information relative to classical systems.
Let's begin with an example. Imagine that we have to store an 8-digit Boolean string on a computer. In a classical computer, we would need 8 bits to represent that 8-digit Boolean string, 1 bit per each digit in the string, with deterministic values of 0 or 1. Now, if we were to use qubits to represent that string and use the inherent values of 0 or 1, it might appear that we would still need 8 qubits to represent that string. At the first glance, there may not appear an advantage of using qubits over bits in the classical computer. However, we can leverage the superposition property to gain advantage over the classical computers. Here is how. Let's take a look at 3 qubits, each in a superposition state. That means that each qubit is simultaneously 0 and 1. In this setup, there are a total of 8 possible states for this 3 qubit system. Essentially, this means that the 3 qubits are in superposition of 8 different states simultaneously. To put it in mathematical terms, the 3-qubit system can be expressed as a linear combination of 8 possible states. The likelihood of each specific state occurring is determined by the amplitude associated with that state. Amplitude squared is equal to the probability. In essence, this 3-qubit system encodes an 8-dimensional vector of amplitudes. If we were to represent this vector classically using the bits, we would need at least 8 bits to store this information. Now, let's step back and reflect on what we just discussed. In classical computers, the information is stored in a physical way. You can actually see it, you can touch it. In quantum computers, information is stored in a form of amplitudes or probabilities of different system states. Imagine if you're flipping a coin that has 70% chance of being tails and 30% of being head. Once you flip the coin, how you can extract that information? You can catch the coin, but then you will see only head or tail. The question how to use and extract information from quantum systems is a big challenge. Of course, you can use qubits to represent 0 and 1 in the same way as bits, but then you do not gain advantage in using qubits and quantum systems. So a quantum computer will need only 3 qubits to represent an 8-dimensional vector. For a vector with 16 digits, we will need 16 bits and only 4 qubits. If we wanted to encode a vector with 2 in the power of 300 dimensions, we will need 2 in the power of 300 bits and only 300 qubits. Keep in mind that 2 in the power of 300 exceeds number of atoms in the known universe. This illustrates the concept of quantum information density, which offers exponential advantage in data representation. But remember the catch. In classical computers, we can easily observe, measure, and manipulate bits without affecting the data that is stored in them. If necessary, we can make copies of this information. In quantum computers, however, the information exists in the form of amplitudes or probabilities of various qubit states. Accessing that information isn't straightforward. But for now, the key takeaway is that this information does exist, and we can use it in data processing and calculations in quantum circuits.
My dear viewers, Alex and I are working very hard on creating quantum wargaming videos for you. Please show us some love and click that like button below. And if you haven't done so already, please hit the subscribe button and ring the bell to join our awesome community and never miss out on the fun. Thanks guys, you're the best.
We have explored a superposition property of quantum systems and advantage it gives quantum computers over its classical counterparts. However, in order to represent any possible number in the quantum system, we will need another remarkable quantum property, entanglement, which will be the subject of our next discussion. Let's take the following example. Suppose we need to encode on a quantum computer vector 1001. As we already know, we will need 2 qubits to do so. 2 qubits have 4 different states, 00, 01, 10, and 11. So we need to set up a system where the amplitudes for the first state 00 is equal to the amplitude of the fourth state 11, and they are non-zero, and amplitudes for states 2 and 3 are equal to 0. So given that the probability of all 4 states must be equal to 1, we will be encoding vector 1 over square root of 2 times vector 1001. The interesting thing about encoding that vector in a quantum computer is that either of these 2 qubits could be 1 or 0. But the second qubit is equal to 0 only when the first one is 0. And the second qubit is 1 only when the first qubit is 1. They are dependent on each other. So can we really physically encode that vector 1001 on a quantum computer if the only thing we can do is to create a superposition of each qubit independently? In this way, these qubits remain independent. And in our case, in order to encode 1001, these 2 qubits have to depend on each other. That property, when qubits depend on each other, is called entanglement. Anna, could you please give us a definition of entanglement?
Quantum entanglement is a fundamental phenomenon in quantum physics where 2 or more particles become correlated in such a way that the quantum state of each particle cannot be described independently of the others, even when they are separated by large distances. When two quantum systems become entangled, measurements made on one system immediately affect the state of the other, no matter how far apart they are.
There is another entangled state, 0, 1, 1, 0. In this case, when one qubit is 0, the other one must be 1, and vice versa. So far, for simplicity, we dealt only with positive amplitudes, but amplitudes could be negative. The negative amplitude squared is still equal to a positive probability. So there are two more entangled states, 1, 0, 0, minus 1, and 0, 1, minus 1, 0. These four states called Bell states in quantum textbooks. It is a proven experimental fact that quantum particles can be entangled. We don't need to know how, but it's important for us to know that we can entangle qubits in quantum computers. The concept of quantum entanglement is very puzzling, even for seasoned quantum physicists. Imagine two entangled particles separated by vast distance. If we measure one of them, that immediately determines the state of the other particle, no matter how far that other particle is. This phenomenon, which Einstein called spooky action at a distance, continues to intrigue. Okay, so with superposition and entanglement, we can encode any vector in quantum computer and realize exponential advantage in data representation. It is time to explore another source of quantum computing advantage, quantum parallelism. Let's consider an example of quantum algorithm. Just as we can construct algorithms in classical computers using bits and logic operators, we can similarly build any function in quantum computers utilizing qubits and logical operations on them. The details of developing these algorithms are beyond the scope of our discussions. Instead, picture a black box that represents such a function or algorithm. Qubits representing the input data are fed into that black box function. We can precisely initialize these qubits, entangle them, and place them in superposition to appropriately encode the input data. The function will also need some registers or qubits, given that we're dealing with quantum computers, for data processing and performing calculations. Now, what do we need to get at the output? At the output, let's repeat all the input data and add the results of the calculations. One of potential applications could be operations optimization for a manufacturing company. The input data might include some uncontrollable variables such as fuel cost or demand patterns for different retail outlets. Also, the input data should include some variables that we want to optimize. Things like the distribution and manufacturing footprint, the pricing of our products, the schedule and timing for promotional events, and so on. In the output, we would want to repeat all the input data or the input scenarios, as well as the target function, which could be the cost or profit of the overall operations for this manufacturing company. Here is the exciting part. Qubits can exist in superpositions, meaning they can represent multiple values at once. For example, a single qubit can be both 0 and 1 simultaneously. Two qubits can be simultaneously 0, 1, 2, or 3, and so on. By exploiting this property, our input data can represent numerous potential scenarios at once. Now, attention. A single execution of the black box function will get us the results that represent all input scenarios at once. To say it in other words, a single execution of the black box function will get us a superposition of all possible results entangled with the input scenarios. This is called quantum parallelism. Once again, and this is very important, a single execution of our algorithm will get us information about all possible values of cost and profit linked to the corresponding input scenarios. However, as we know, the data is encoded as superposition of possible scenarios, of superposition of possible qubit states. We can't simply read the data and get the results. Just simple reading the data will give us a random input scenario with corresponding values of cost and profit. Luckily, there are techniques involving quantum interference, and we will not get into details, physical details behind it, but these techniques do exist that can raise probability through changing the amplitudes of different qubit states. These techniques can raise probability of the desired outcome, being that lowest cost or highest profit, close to 1, and reducing probabilities of all other outcomes down to 0. Once we have done that, we can actually then read the qubits and receive the information about the optimal results of the target function, lowest cost or the highest profit, and the corresponding values of the input scenarios. Input scenarios that allow us to maximize our profit or minimize cost.
And now, let's summarize what we have learned in today's session. Quantum computers utilize qubits, capable of representing 0, 1, or a superposition of both. Qubits can be entangled when the value of one qubit determines the value of the other. Superposition and entanglement allow qubits to offer an exponential advantage in data representation. Quantum parallelism, a distinct feature of quantum computing, allows for evaluating multiple function values for different inputs in a single run, offering a massive computational advantage. As with all revolutionary technologies, quantum computing has its challenges. In subsequent sessions, we'll explore the hurdles in building quantum computers. Until then, goodbye, and stay tuned for more.
Quantum computing, it's a game changer. Shift in the paradigm, rearranger. It will shape the future like no other. Step up your game.